Hello, I am audible. Hello. Please respond. Please respond with your mic, please. Okay. Today, good morning, one and all. Today we can discuss the last time harmonic functions we are discussing the last week. One theorem we have to discuss is it today also. The continuation process. If none of Z1, Z2 and Z1 into Z2, Z1 comma Z2 and Z1 into Z2 is non-positive real number, then we are taking here log of Z1 Z2 is equal to, so in the multiplication process we can write here log Z1 into Z2, we can write here log Z1 plus Z2, I am division that here plus also 2n 2 pi I, we are writing here 2 pi I 2n pi I 2n pi I, we are writing a where is equal to n, where n is equal to -1 comma 0 comma 1 I am taking here. So this is a fundamental statement here. Now I am taking the proof here. So here log of Z1 Z2 multiplication part, that is log of Z1 Z2 plus I of argument of Z1 Z2. See here, this is a real part and this is an imaginary part. So I'm separating log Z1 and Z2 here. I'm writing here log of Z1 with modulus of log Z1, modulus of log Z2 plus I of argument of Z1, imaginary part, argument of Z2 plus 2 pi 2n pi 2n pi, it is a value, it will become here when where n takes, what is the values what taken here I already told in the problem, where -1 0 comma +1 I am taking here -1 to +1. So this is here we are writing here, therefore log of Z1 log of Z2 plus 2ni pi. So 2ni pi means this is the imaginary part I am multiplying here, 2ni pi. So therefore I am taking n is equal to -1 comma 0 comma 1. So -1 to +1 I am taking here. So therefore the exponential function cannot inverse. So exponential function cannot have an inverse. So therefore not, it is 1 to 1 or not 1 to 1. Tell me, anyone is there? It is 1 to 1 or not 1 to 1? It is not 1 to 1. We have constructed the inverse function. So restricting the domain. So what is the restricting the domain? I am taking here Z. That I am taking here restricting domain minus pi less than or equal to imaginary object less than or equal to pi. I already told you minus pi minus 2 plus minus pi less than or imaginary object less than or pi. So we can call the principal branch of the logarithm of the log. So almost all these properties are except the logarithm functions here. So this is different such regions where exponential function is 1 1. We can define my possible logarithm functions. So therefore we can this one we have to take a log z1 plus z2 plus 2ni, that is 2ni pi minus 1 to 0 1. Any doubt ask me in this problem, in this theorem. Otherwise I will go another definition. Please. Okay. A region or such that exponential function is 1 to 1. So 1 to 1 means 1 to 1 and on to here, but 1 to 1 is R, but no region properly containing R, no properly they are R. So fundamental region is also called as exponential function, this one. Another definition we will take here. And let alpha be a complex number and log r the branch of the logarithm, a branch of the logarithm associated with the fundamental region R. So in this R we are taking let alpha be a complex number. So the branch of log of the branch is a logarithm already. You know that it is associated with what's the region here given the R. So therefore we have taken the exponential function that the function z stands to exponential function that is alpha log r to z. This is z in the domain. What I already told in the domain of log r is called as this z to exponential of alpha log r. Alpha or z in the domain we can take as the power function. So therefore, we also the term a branch of the alpha in power in which emphasize that the branch of the algorithm that has been involved here is this. So what is the z? Z stands to exponential of alpha to alpha log z. Alpha log z we are taking here. The principle of the branch algorithm is called as the principle of branch of the alpha power. We can call as the branch of the power of the alpha of the power also we are taking here. This is the one fundamental here. The dimension should be the bring. Mind the definition x power n. X is a positive real number and alpha is a irrational number that is a real number. So x power n to that is we can write here x e power a log x also we are taking it. So suppose we are taking an example here. So that the numbers z power 1 minus here, so that the numbers I am writing here. Therefore, n is a being a positive integer obtained by the multiplying the particular nth root of z by the nth roots of I. That is the one. So taking here, you know that log of r. You know that log of r is a branch of the logarithm. You know that the let z be the domain. Let z be the domain of log of r. But the possible of values of z1 minus n. So therefore we can write here expect exponential function of log nz plus 2 mi pi by n. 2 mi pi n. Already I told you that is n. This is I'm taking log z 2 n pi. So what is m? Anyone tell me what is m? Anyone is there in the class? What is m? Yes. What is m? So m is integer. So therefore m is integer here in imaginary part. So that the distinct value of z for I m given by we can write here I m. We can write here this one. So therefore the m is equal 0, 1, 2, 3, 4, 5, and also up to the n minus 1 we are taking here logarithm of that is exponential function of log n by z by n. So therefore exponential function of log r we are writing to the function by n exponential function we are taking here 2 pi I by n we are taking here. So therefore exponential function of log n by z by n log n by z by n exponential here 2 into n minus 1 pi I 2 into n minus 1 pi a 2 into n minus 1 into pi I by n we are taking here. But exponential function of log r by z the particular nth root we are taking here. Particular nth root of z that is 1 by e 1 comma e 2 I z. That is the value of we are taking nth roots of 5. The values are we are taking here. But what we are taking here, log r by z we are taking here. Z stands to exponential of alpha log z we are taking here. On that condition, we are taking here exponential of log r z 2mi pi 2mi pi, that is m integer. So on that condition, m is a 0, 1, 2, so on n minus 1 we are taking it, and that condition exponential of log r z by exponential of, that is the condition we are writing here. N minus 1 I am taking here in place of that value, n place low. In place of n, I am taking n minus 1, 2 into n minus 1 pi by pi. That's the values of this one. So therefore, this is our nth roots of pi we are taking here. Please, any doubts, ask me. Otherwise, anyone is there or not, I'm not know what is the principal, what is the principal value of I. What is the principal value of I? So therefore, log of I is equal to I pi by 2. Thus, e power log. What is of e power log of x? What is that value? What's the value? Anyone tell me, please? Log of e power of log t is equal to e power of minus pi by 2. So the value, the principal value of that is e power of minus pi by 2 we are taking here. So for all these one, you have to take the possible values also. You have to take here. Now we will go to another unit here. So another one problem is solve the equation cos z is equal to 2. Solve the equation cos z is equal to 2. Solve the equation cos z is equal to 2. So we know that cos z is equal to 2 and z is equal to, we know that x plus I y. Real and imaginary part we take it. That is, you can take that cos x, hyperbolic function I am writing, cos x cos hy minus I into sin hy is equal to, so that is the imaginary part only, that is the only imaginary part here, that is 2 I am writing here. Sorry, cos x cos hy minus I sin x sin hy is equal to 2. So this is the equating the real and imaginary parts. We have know that cos x cos hy is equal to 2. Cos x cos hy. Why? Because this is the real part. This is the imaginary part. The imaginary part I am writing here. That is a 0 minus I sin x sin hy is equal to 0. The total is equal to 2, but the real part is 2, but the imaginary part is 0. Thus, I am substituting y is equal to 0. What is x value here? Sin hy is equal to 0. Then the sin hy is equal to 0. I am taking here. What is sin x value? What is sin x value? 0. The only solution here, the only solution to the equation y is equal to 0 is 0. So that y is equal to 1. So therefore y is equal to 1 we are taking here. Therefore cos x is equal to 0. Y is equal to 1 means y is equal to 1 means we are taking here. So therefore cos x, therefore y is equal to 1, cos x z is equal to 2. Cos x is equal to z we are taking here and has no solutions here. Therefore also the same here, x is equal to 0. Therefore x is equal to n pi cos x is equal to z. Therefore cos x is equal to so therefore cos x is equal to z we are taking here. So therefore sin x is equal to 0. Therefore sin x is equal to 0. Therefore what is x value? Please respond amma evaru unte. Please x is equal to n pi. 1 is there. Now I am showing. Please. X is equal to n pi. I am audible? I am audible? Hello? వినబడుతుందండి? So x is equal to n pi, where n is an even integer. You taken x is equal to 2m, n is equal to 2m. N is 2m. This is turn implies the cos y is equal to. So therefore, cos hy, the hyperbolic function is equal to cos hy is equal to 2. So therefore, I am writing e power x plus e power x is equal to 4. That is, we are writing e power 2x minus 4 into e power x plus 1 is e power 2x minus, that is e power x plus e power x e power 2x. Then 4, that we are writing 4 minus 4 into e power x plus 1 is equal to 0. So this is the one condition. The quadratic equation I am writing here. The quadratic equation. What is the quadratic equation? The quadratic equation. The quadratic equation I'm writing here, e power x has roots here. So we can take the 2 plus r minus 3. Why? Because b square minus 2ac by 4a, that is the condition I'm using here. That is a condition, that is 2 plus r minus root 3 here. So therefore, y is equal to, I'm taking here log of 2 plus r minus root 3. So therefore, what is the cos z value? Cos z value? Cos z value? So cos z value is equal to 2. Therefore, cos z value I'm taking here. Cos z value is equal to t here. Therefore, z is equal to 2m pi. Z is equal to 2m pi we are taking here. Then I log, already we know that there's a value here, 2 plus r minus root 3. When this is possible, if cos z is equal to 2, if cos z is equal to, then only it is possible here. So therefore, we can take that where m is an integer we are taking here. So this is the one. Another problem we have to learn here. Show that cos z bar is equal to cos bar z. Cos z bar is equal to 1 by 2 exponential of I z bar plus exponential of minus I z bar that is 1 by 2 into, that is exponential of, I am taking total one minus I z, therefore exponential of, this is multiplication, that is subtraction into, since exponential of z I am taking here, so exponential of z we can write here exponential of z bar, exponential z also we can write here, so exponential of z bar is equal to cos of z bar, so the condition is satisfying here. This is a basic fundamental. So but fact in this complex function, its properties are very similar. Those are the real exponential function which agrees that the function are the real axis named in the complex exponential function. So notice that one significant of which different of a real exponential function also we know that it is not necessarily one, but even though it is a periodic and all these functions are, you have learned this. Any doubts, ask me in this unit, please. Any doubts, please? Otherwise, we will go another unit. Okay. Next unit, complex integration we are taking here. The complex integration, we can Jordan curves and contours, rectifiable curves, complex integral, smooth curves. We can learn in this unit. What is a Jordan curve? So we are in the Jordan curves we are taking here. The Jordan curves, the definition here. Consider, I am writing in the definition. Consider two continuous real functions. What is the definition of two continuous real functions? What is the two continuous real functions? Tell me what is the two continuous real functions? Please. Two continuous real, what is it? Two continuous real functions means f of x and g of x. We can take here f of x and g of x are functions. There is a defined or that real numbers whose graphs are can be drawn without lifting the pen or paper, meaning they have no jumps or any breaks is not there. So it's what are the real functions means a real function whose input and output the both are real numbers only, we can take the real function. What is the continuous? A function of continuous mean a point as that the input approaches here, that the point output also approaches the function of the that value here. More familiar formally here, x is equal to the of f of x approaches equal to f of a, that is f is defined here. So therefore, that is a function what we are taking here. So real valued function, therefore x into t. Therefore, x into t and y xt and yt of a real variable real variable here, uh, t ranging here overall values in a closed interval. What we are taking here, a less than or equal to t less than or equal to b are taking here. The parametric equation we can take here, x is equal to xt and y is equal to y of t. So therefore, a less than or equal to t less than or equal to b. That is the condition we are taking here. So defines a continuous curve C made of all that xt and y comma t. So we can take here a less than or equal to t less than or equal to b, a less than or equal to t less than or equal to b. We are taking here. You can write the equation. This is the you can write the equation here in a single complex parametric equation z is equal to z of t. So therefore, a less than or equal to t less than or equal to b, z is equal to z of t. So z is equal to x plus I y. I'm taking here an imaginary part. Therefore, z of t is equal to x. Xt that is equal to x of t. We are taking that the real part and imaginary part I into y into c. So therefore, this is the you can observe that the z is equal to zt trace out c, taking the initial point za and the final point zb. The parameter t vertices are from A to B we are taking here. Definition we are taking here. Some definition. A curve is said to be closed in the initial point z of A and final point zb coincide. See here, a curve is said to be closed of the initial point ZD and final point ZB. Initial point ZD and final point ZB coincide we are taking here. So ZA is equal to ZB we are taking here. We'll be returning the same points here. But all the points of the corresponding the parameter, we know that ZA and ZB, but the corresponding of the parameter is equal to T. The curve C is called as the curve C also called as ARC, arc. If not, it is not closed. So Z not closed, we can Z not A is equal to ZB. ZA not equal to ZB. I think here. So therefore, we have discussed it from the earlier definitions, we can take here. We can recognize that the curve of the continuous image of closed interval of the real numbers. Interval of the real axis being the continuous images of a bounded closure set. A curve is unnecessarily, you can know that there is a bounded or closure here. But even though you can think that the curve having different R orientations according as we trace the curve. So from A to B at B to A, if B greater than A to B, B to B, B greater than A, and we traverse along C, from A to B, we call the direction of C all positive numbers of C here. So this is a oriented curve of the sea said to be traversed in the direction of the increasing sea. So also almost increasing sea we are taking here. So, but we traverse of the along see the opposite direction of the increasing of the sea. We denote direction travel sea. So therefore, the curve C is a traversed in the negative directions. We know that. So one definitions we have to learn in this unit. What's the definition we have to? One definition we have to see. A set E of points. Any set, we will take any set E of points here in the complex plane. In the complex plane is called an arcwise. Is called as an arcwise connected set. Connected set means we are taking a connected set. We take a set of E points in the complex plane is called as arcwise. Every connected set here, if every pair of points, if every pair of points, if every pair of points are taken Z1 and Z2, we are taking here. E can be joined by an arc consisting entirely points that is E here. So thus an arc with the initial point Z1. You can know that the initial point Z1 and the initial point Z2. Thus the arc is initial point Z1 and Z2. We are taking here as initial point and final point. So next one, another definition we have to learn. So set G, the complex plane is said to be domain. If it is open and if it is open and connected, it is a definition. I will explain here. A set G, we know that set is the complex plane, said to be the domain. It is open and bounded. What is a domain? Anyone tell me what is a domain? Domain definition. Domain. So in the domain definition means we are taking in a domain the set of values we are followed into our function, plugged in our function. The set of the x values that is f of x, the range of the function is set of values. The function is assumed here. The set is all the values of the function. After we plug the x values also, we know that here we are taking here. So another one definition here. A domain G, or more generally, the set of complex name, we know that here also said to be the bounded. Already done the domain also then is a bounded also if G is contained. If G is contained here, the sum circle and center the origin of the radius are greater than 0. Otherwise, G is said to be as unbounded. And there's so many definitions here. So you have to study it. We can a simple closure curve defined as a Jordan curve. A simple closure curve as called Jordan curve we are taking here. So that is a Jordan curve also we can take here. Simply connected domain. So simply connected domain we can take here. Simply connected domain, a domain The domain G is said to be simply connected where G contains closed Jordan curve, while that simple closed curve is defined as Jordan curve. In the complex domain, G also contains that is C comma I C. So otherwise, G is said to be multiply connected. So this is this one. This is a G here. So this is a complex plane. The total dots. This is simply connected. This is a simply connected domain. They are taking here this one. If x and y and y and t thus zt, if x and t and y and t and z and t have continuous derivatives, a continuous derivatives here, a less than or equal to p less than or equal to b, a less than or equal to the curve is said to be a smooth curve, or r is also known as the regular, it is a regular curve also we can take there. The regular curve also note that arc, the curve which is completed a finite number of smooth arcs are called piecewise or sectionally smooth curve or path. A continuous Jordan curve containing the finite number of the number negative arcs is called as contour. So this is one. I will give a graph here. The point on your graph. This is called as continuous curve. So now I am taking the simple closure curve, that is the Jordan curve. This is a Jordan curve. This is a simple closure Jordan curve I am given here. This is the one 1 to 1 we have to find it. E of C also we can take it this way one point of view. So one example we have to take here. Would G be the domain defined by G be the domain defined by Z less than 2 figure. By definition of the earlier one we learned here, G is a simply connected domain. So therefore G is reasonably defined here. Less than of modulus of less than z is equal to less than z we are taking here. So there is a simple curve C lying with the G cannot be the strength of the point without leaving Z. So G is multiply connected. We know that here. Someone graph you are taking here. This I am taking a graph. This is T. The modulus of Z minus 2 is G. This is C. So the X and Y Z is a G here. All the dots of this one connected here. So this is a simply connected domain here. That is colon Z less than 2. That is simply connected domain. Simply connected domain here. Then multi-connected domain we have take here. Multi-connected domain. This is a circle of this one. This point 1 to this is the point of this circle. These are 2. The modulus of z is equal to 1 and 0. So all the dots of this graph here. So this is called C here. This is called multi-connected domain. Multi-connected means there is a two circles is there. That is 1 less than or equal to modulus of z less than 2. This is a multi-connected graph also we are taking here. And multi-connected region we are taking the graph. I'm taking the small one here. This is called multi-connected region here. So in the multi-connected region we are taking here, you can inner sum of the figures. So the both are simply connected in the course does not have any holes, while the multiply connected region has the multiply connected region. So the above multiply 1 and 3 holes in them here. So from the figures of the earlier figures, the interior of any circle, the simple connected region or domain are the points of the variant concentric circle called an annulus, and the multiply connected which is a domain also we are learning here. Then rectifiable curves. 55 bubble curves. In the let the z is equal to we have to take here. The z is equal to t is equal to xt plus I into y into t. So therefore that is a real in my part. We know that a less than or equal to t less than or equal to b. Define a curve C in complex plane here. So suppose that interval a comma b is derived in subintervals here. Tk minus 1. Tk that is k is equal to we can take here 1, 2, 3, 4 and so on. We can take here up to n. The set p is equal to t ij to the C1, T2, T3, Tn up to is called as a partition of the interval of a comma b. You can write a partition of the interval a comma b. You can write here. How you can we can observe that here there are n minus intermediate positions, that is I1, I2, I3, I4 and so on. In we can take in here. Lying between the end satisfies that the inequalities. For alpha is equal to a is equal to we can write a is equal to T2 less than T1 less than T2 less than Tn minus 1 less than Tn is equal to b. Again, I'm telling here Tn less than T1, Ta less than T1 less than T2 less than so on, Tn minus 1 less than Tn is equal to b. T1, T2, T3, T4, Tn minus 1 is in this is there. So the corresponding the partition, therefore the curve C is individual, the curve DC is individual, then n arcs here. So therefore Sn is equal to the take here. Sk is equal to we can write it Zk minus 1, that is k is equal to 1, 2, 3 and so on. Then we are taking here. So Z is equal to 1, 2, 3, then we are taking here. Where Zk is equal to lambda of Tk, that is equal to k. of 0, 1, 2, and so on. With a P also it is 0, 1, 2, n. The final point and the initial point and final point taking here. Therefore, the final point here. Each arc excellent the last one and so forth here. So the initial point of the next arc. We obtain a curve by joining the point z0, z1, z2, z3, z4, and zn to be the next of the straight line segment. Then this is known that the polygonal curve also is known that. So therefore, the segment of AK is the design by the end of the points that is here. So therefore, the limit point of let the point of A, length of A we can write here as star. The star is equal to summation of R is equal to 1 to n summation of ZA minus ZR minus R. So therefore, we are taking here ZK minus 1, ZR minus 1. ZK minus answer we are taking here. The curve is said to be rectifiable. The when is rectifiable, we have to write here. The curve is rectifiable, it can be said to be rectifiable. So therefore, suppose C is equal to the summation of P we are taking here. Summation of I is equal to 1 to n. Zk minus 1 is equal to 1. I less than infinity the condition we are taking here. Where is the condition here? Where the upper and the bounded and denoted by the symbol supremum here, symbol supremum here, which is all overall the possible partitions P of the interval A comma B. The length of the curve is defined by the negative number I we are taking here. However, on the other hand, we the, the other hand of the scheme of T become the arbitrary large of the suitably chosen of the partition T. Curve as an ambiguous, non-rectifiable, and score the course of T. So therefore, writing therefore non-density all of you are instructed are instructed here. In fact, accepted or infinite of the length of the we say here. And diagram is this. Z1, Z0. Therefore, we are taking here, in the figure we are taking here, the rectifiable curve, see the polygonal curve. We are taking here this one, Z4, Z4, Z5, this is A, this is C, this is curve H1, H1 taking here. The phase for the polynomial curve n is equal to 5 we are taking here. A property rectifiable curve we are taking here. Let's see we are taking here. Let's see any curve defined z is equal to zt. Z is equal to z of t. A less than or equal to t less than or equal to b are taking here. Suppose C is the number of between A and B. Let two occurs of C combined by varying T in intervals A comma C we are taking here, and the C comma B I am taking here is denoted by we are taking C1 and C2 respectively. C1 and C2 respectively we are taking here. In the following the result has been follows here. C is rectifiable and C1 and C2 here is almost rectifiable conversely. So for the case of the I is equal to I1 plus I2, I1 plus I2, we are taking here. So L1 and L2 is denoted by the length of C1 and C2 respectively here. So note that here Z is equal to Z of T. So continuous and A comma B. So the result of the follows the case. The continuous function obtains its bounds in a closed interval. So how it is possible? You have to learn this one here. So that is Z is equal to T continuous and A comma B. We know that here a continuous function obtains here its bounds here. Then another one, complex integral. Complex integral. So therefore complex integral here along with the okay. Complex integral, the complex integral along complex integral along on oriented curve we are taking here an oriented curve we are taking here. Let us the oriented curve already I told here the Jordan curve is told here. So oriented curve is z is equal to zt. Z is equal to z of t we are taking here. So a less than or equal to t less than or equal to b. Assume that f is any complete function. So therefore a is equal to t0, t1, comma t2, and so on tn minus 1, then ti, and so on tn minus 1 and I1. Therefore, here T0, T1, T2, Tn minus 1 and Ti minus 2. So, and we are taking what we are taking here T0, T1, T2, T3, T4, T5, T6, and so on Tr minus 1 and Ti and so Tn minus 1. This is called as B. This is called as B. We are taking the partition of P of B. But alpha is equal to any alpha lying between Ti minus 1 Ti. So the right is ZTi. So therefore ZTi is equal to Z1, Z alpha is equal to zeta of Ti we are taking here, zeta of Ti we are taking here. So therefore we know the formula of the sum we are taking here. S is equal to Z1 minus Z0 f of zeta 1 and f of zeta 1 minus Z minus Zi minus 1 f of zeta. So what we are taking here, so zeta 1 then Z1 minus Z2 zeta 2 and Z1 Z2 minus Z alternate zeta 2 and so on and taking here this one up to Zn minus 1 f of zeta n. So zeta n we are taking here. So therefore the simplification of this one, summation of I is equal to 1 to n I minus zi minus 1 f of zeta I we are taking to each partition p and the choice of alpha the corresponding the sum of s we are taking here s taking here. Oh, Z minus Z I minus 1 f of zeta we are taking here. So therefore, the each partition of P pi choice of alpha the correspondence is sum of S we are writing here. Another one definition we have to learn here. Another definition we have to learn here. The function f of z is said to be integer on over C. So therefore, over on C, if there exists a number of I such that each epsilon greater than 0, one definition I'm writing here. That is the function f of z said to be integrable over C if there exists a number I such that each epsilon greater than 0 there exists a delta greater than 0 we can take here. So we can take here this condition is satisfied here. Modulus of s minus I less than epsilon. Modulus of s minus I. Modulus of s minus I less than epsilon we are taking here. S minus epsilon. For every partition P, for every partition P whose norm less than the delta for every choice of alpha, for every choice of alpha we are taking here. So this I is called as line integral or simply the integral of f of z. So this is we can take the integration of c f of z is equal to 1. Integration of f of z dz is equal to 1. So that is the basic fundamental with the complex number integration of c, that's the value. So but also with the counter of the integral of z with the curve or counter denoted by integration of c f of dz, integration c f of z dz. You can take the quantity here, limit of p stands to 0 here, summation of I is equal to 1 to n zi minus 1 into zk. So that sorry zk also we can take it zk minus 1. So we can take zk minus 1 into zk. So therefore limit of p stands to 0 is the modulus of p stands to 0 is. So why? Because this is fi we are taking here, f is integrable. So where the alpha k is equal to z, therefore st is called as the approximating sum of the integral we are taking here. Approximating sum of the integral. Then basic properties of the integral. So in the basic properties of the integral, what we are taking here, basic properties of the integral. So basic properties of the integral, first property I'm taking here, property one I'm taking here. Suppose that f of z is equal to 1. So integration of f of z dz. So integration of c z, do I know that f of z is equal to 1? So we can take here z1 minus z0 I am written here. So where z1, zn, z0 here? The values of z. So z values zn, z1, all the values are only z at the endpoints of the curve C. So we can write z is equal to z is equal to t. But where is the condition we are writing here? A less than or equal to t less than or equal to b. Let us write the partial sum. Let us write the partial sum we are taking here. Sp is equal to summation of I is equal to 1 to n I am taking here. So zi minus 1. So that is f of zeta I also am writing here. So zi minus 1. But what the partial sum give? P means partial sum. So therefore f of z I am writing here the property 1 condition for all that f is equal to 1 for all that we are taking here. So f of zeta is equal to 1 for all. For all we are taking here f of zeta is equal to 1. So therefore the sum reduces here. Therefore the sum reduces here. It's summation of I is equal to 1 to n zi minus 1. So therefore the zi minus 1 already I told in the beginning that is zn minus z0. So zn minus z0 means, so where we are taking here zn and z0 are the fundamental functional values and z representing the final point b and the initial point a respectively. Hence my definition of the complex integral we have taken care of the definition integration of c of dz. We know that the integration of t c is zn minus z0, where z and z0 of the values of the z only the endpoint of the curve c. It is already I told a less than or equal to t less than or equal to b the condition. The condition is satisfied in property 1. Now we are taking the property 2. In property 2, we are taking here f of z is equal to z integration c f of z dz integration of c f g, z is equal to 1 by 2 of zn square minus z naught square. Zn square minus z naught square I am writing here. Suppose we are taking f of z is equal to z1 integration of c f of z is equal to integration of c z integration c, but z dz we are taking here. So therefore integration of f of z dz is equal, what we have to write here, zn square minus z naught square. Second condition also integration of c fz dz law 1 by 2 zn square minus z naught square. Zeta I am taking here is equal to zi in zi where what I value is equal to 1, 2, 3, 4 and so on, and it is approximating sp. So therefore sp I am taking here summation of I is equal to 1 to n zi minus 1 into zi into zi minus 1 into zi we are taking here. Similarly we are taking zeta I. Similarly we are taking zeta I into zi minus 1. I is equal to 1 2 so on n I am taking here. So there's the partial therefore already I told that p is the partial sum. So s dash p is equal summation of I is equal to 1 to n. So first partial I am taking zi I minus 1 into zi I minus 1. The first one we can take in here z1 minus zi minus zi minus 1. Here s dash p is equal to zi minus 1 into zi minus 1. So that is called as s dash p. We are taking here as the function f of z is equal to z, as the function f of z is equal to z is continuous. So it is integrable and definition both approximating sums sp and sp and s dash p I am taking here to the same limit of the dash modulus of p dash 0 integration of c f dz and also sp and s dash p. The first property and second property I am adding here. Summation of I is equal to 1. That is and zi minus 1, then zi plus zi minus 1 and 2 I am adding here. So see here summation of I is equal to 1 to here. Zi minus 1, so write zi minus square, zi square plus 1. So a minus b to a plus b, a square minus b square. Z square minus n, Z square naught. Both are taking here. Integration of C f of Z dz. So integration of C dz. Integration of C dz, that is 1 by 2. Limit of t stands to 0. I'm taking here. That is Sm plus S dash t. So this is the function f dash z. I'm taking here as Sm plus S dash t. That is the above value. That is 1 by 2 into Zn Zn square minus Z naught square. So Zm here Zn square Zi square minus Zi minus n whole square, that is called, we can write Zi square minus Z naught square, that is 1 by 2 into, we can write that is the property 2. Then property 3. Property 3. C is a closed counter. Integration of C dz is equal to 0. Integration of Z dz is equal to 0. Integration of Z is equal to 0. Integration of C dz Z is equal to 0. We are taking here. So since C is close, the initial point, the final point of the coincide, we are taking here. We know that the Z and Z naught we are taking it. Therefore, the properties 1 and 2. How we can possible here the some properties without any explanation here, the fundamental properties of the integral, the rectifiable curve, how we have to learn here. Then property 4. Property 4 we are taking here. The property for integration of C f of z dz is equal to minus integration of C f of z dz we are taking here. Where minus C represents? Where minus C represents here? C is transverse in the properties of direction here. C is the transverse in the properties of the direction we are taking here. So therefore, automatically minus C may represent the curve C. Already we know that here. Then property 5. The property 5, suppose C equivalent to union I is equal to 1 to n, then C1. We have to final the curve. We have to final points of the curve CK. So CK is the coincides with the initial points of the curve. CK I minus 1 is equal to K is equal to 1, 2, 3, 4, and so on n minus 1. So already I told C1, C2, C3 up to CK we are taking, that is the curve we can take here. Therefore, we know that integration of C f of Cj is equal to integration of Ck, that is integration of fz dz, integration of f1 dz, and so on up to integration of Cn f of dz. And C1, C2, C3. These could both are the nth condition that we have to take here. This is the fifth condition now. Now I'm taking the property of sixth condition I'm taking here. See here integration of C K1 f of f1 z and K2 f of z and K3 f of z and so on plus Kn f1 z. So we will get the summation of I is equal to 1 to n f1 z. So where f1 z, this is the f1 z I am written here. So f1 z, f1, f2, f3, f4, f5 and so on, fn are the complex functions which are defined in continuous in on complex plane. So therefore K1, K2 are arbitrary complex constants that we are taking here. One example we have to take here in the six properties learned here. Then one example we can take here. Evaluate integration of C modulus of Z square. Z in the circle of C, Z is equal to gamma. So therefore the solution, the parametric equation of the curve is, the parametric equation of the curve is, this is called gamma into e power I theta, 0 less than theta less than 2 pi 0 less than 2, theta less than 2 pi. And I is equal to integration of C, z square of dz, integration of 0 to 2 pi. I'm taking integration of 0 to 2 pi. I'm taking here, that is gamma into r into e power I theta whole square, gamma into y e power I theta d theta. Integration of z square dz, then r into e power I theta whole square, then r into e power I theta d theta 0 to 2 pi on into e minus theta e power I theta e power I theta d theta. Then gamma cube 0 to 2 pi e power minus 2 pi theta e power I theta d theta I'm writing here. So therefore I into gamma cube 0 to 2 pi e power minus 2 minus I theta d theta. So minus I theta d theta, correct? So the integration I into gamma cube. So after this integration e power minus theta by minus I. The simplification of that is 0 to 2 pi I'm applying here. 0 to 2 pi lower bound and upper bound I'm applying is equal to 0. Let zt is equal to xt plus y into it. A less than or equal to c less than or equal to b is flexible curve. Please depend as f is equal to z u of x comma y I into vx comma y the continuous on c. So that is the real and imaginary part. So integration of c f of z dz, integration of a to the u of x of t into y of t I am taking here. Therefore x dash t plus I y dash t I am taking here, that is dt. Plus I into the imaginary part, integration of a to b v of x t and y t, that is here. Then x dash t x dash t plus I y dash t. So this is the function what we are taking here. Imaginary u of x t and y t, then x dash t and plus y dash I y dash t. Then the imaginary function x dash and y t and x dash t plus I y dash t. These both are a to b. We are taking care of the integration of these values here. So then the smooth curves we have done here. Smooth curves. We are taking the smooth curves here. Just a minute. Let C be a smooth curve. We know that the definition of the earlier, that is represented by a complex function. Z into t is equal to x into t plus I into y into t. A less than or equal to t less than or equal to b. We know that. Let f be a complex function. Let f be a complex function. Continuous every point on z t of c. So p of a comma b. So we can take the p of a comma b, that given a is equal to t0 less than t1 less than t2 less than and tn minus 1 less than tn is equal to b. We are taking here. Assume that here assume P1 is less than or equal to SP less than or equal to P minus 1 less than or equal to SR less than or equal to F. From the sum we are taking here, SP is equal to summation of R is equal to 1 to N F of Z of SR Z of PR and Z of PR minus 1. So see here, this is the Riemann's triangle. Riemann trivial sum becomes here. SP I'm taking here. Summation of n r is equal to 1. That is a zeta r I'm taking here. Then z r minus 1. So zeta r is equal to z of s r I'm taking here. And also z r s minus 1. So I'm taking the values of xt plus I by t less than or equal to t less than or equal to b. So ZSR and this is the existing of the direct variable case, and the smooth curve is rectifiable is length here. What is the formula? T is equal to integration of T is equal to integration of a to b. So T is integration of x dash of t whole square with y dash of t whole square dt. Integration of a to b, the dash of t. So this is integration of x dash t whole square plus y dash of t integration of a to b z dash of t dt. So also p of x comma y Q of x comma y we are taking here. P of x comma Q of x are two real functions different continuous on every point. That is equal to z of t is equal to x into t plus I into y into t I'm taking here. In the complex number that will be shown that summation of I is equal to 1 to n. I'm writing here that is P of eta k comma eta k then is xk comma xk minus 1 plus q into zeta k minus meta k, then yk minus beta k you need as a common. That is the approach of the unit limit is denoted by integration of c of x times t, then y of t of x, then x dash t plus t of x t, then y of t, then y dash of t. ఇక్కడ x dash t, ఇక్కడ y dash t. So we can define here, integration of c f of z dz as Riemann's integration of a to b z of f of z of t z dash of f t dz. We have to take this function of this one. So another problem example we have to see another one problem. Evaluate integration of dz by z minus a. Using the definition where z minus a is equal to r. Solution we are taking here. The parametric representation of C is given by it is equal to zt. Replacing the order 0 less than 3 less than or equal to 3 for the condition. So now z dash t dz by dt I'm taking here. So dz by dt r into e power it, r into e power it. Hence by the formula is given the integration of t dz by z minus a So here we will learn this problem, evaluate integral, integration of dz by dz, where gamma denotes the square, describes the action, so by the sense with the figures, the parallel of the converse of the origin. Tomorrow we will learn this problem. Any doubts, ask me in this regard, please. Today's one. Please, any doubts, ask me. Or we'll come today's class. Otherwise, we can ask me. I will wait.